This is Anand from the University of Illinois to present view generalization for single image texture 3D models. This is joint work with Aisha, Gwilyn, Andrew and Brian while interning with NVIDIA. From a single 2D image input, our goal is to infer a high quality texture 3D model, a triangular mesh and a texture map. We want the infer 3D model to display good view generalization. That is, the image when rendered from source view should look like the image input. More important, new views of an inferred model should look real and be consistent with the image input. Previous approaches struggle with view generalization. The output of CMR appears to be squashed. In comparison, DIBR produces smooth 3D models, but it too struggles with view generalization. That is, the novel views are geometrically inconsistent and lack texture details. We achieve view generalization by a controllable deformation approach. We also introduce two new cycle consistency losses, a rotation GAN cycle consistency for improving the shape and a texture mesh alignment cycle consistency for improving texture. Both these losses, when combined with our controllable deformation, significantly improve view generalization. Instead of deforming meshes in their 3D XYZ world coordinates, we deform meshes in their projected 2D UV coordinates. This 2D UV deformation allows us to control the extent of deformation by simply changing the degrees of deformation or the spatial resolution of the predicted UV deformation maps. Having controllability over deformation helps for different object categories with varying degrees of rigidity. For example, cars are more rigid than birds. A higher deformation yields a more flexible model that is useful for birds. See thin structures like the beak and legs of the gull in the top row for the 3D models with high deformations. Similarly, a lower deformation yields a less flexible model that is more suitable for cars. Therefore, for rigid bodies, we use a small degree of deformation, and for non-rigid bodies, we use a large degree of deformation. Next, we show the first of two consistency losses that improve view generalization. Our rotation GAN cycle consistency helps improve the geometry of infer 3D models. From a pipeline, we render images from two views, one from the original view and another from the novel view. From the predicted novel view, we re-render a new image back to the original camera view. The original rendered and re-rendered images must be consistent with the input image. We also train a GAN to discriminate the image input as real and the novel view image as fake. This helps improve the realism of inferred novel views, resulting in improved geometry of inferred 3D models. Our next loss enables learning useful priors by sharing spatial texture information across inferred models. Given two input images, we first infer their corresponding mesh and texture map. Next, we swap texture maps and render two intermediate images. We infer texture maps for these two intermediate images. Finally, we swap texture maps one more time and render two images with their original meshes. Our key intuition is that the final rendered images, that is after two swaps, must be consistent with the original input images. This consistency encourages the texture representation to store details like headlights at a specific spatial location in the texture map. This facilitates sharing texture details across 3D models even for views that are not visible. Here are a few qualitative results comparing our approach with DIBR. Our results with and without consistency losses are in the last two columns. Both controllable convolution deformation and consistency losses improve view generalization, and when combined perform the best. The last column shows superior shape consistency and realistic texture details even for occluded regions. Particularly, see the headlights in the top row and taillights in the bottom row. For more qualitative figures and quantitative evaluation, please refer to our paper. To conclude, our method displays improved view generalization by using a controllable deformation approach combined with two novel cycle consistency losses. This results in high fidelity texture 3D model synthesis only from a single 2D image. Thank you.